right. Hello, Internet. We are live.
Hey, everyone. Welcome to episode 13 of the Stanford MLSys seminar series. I'm Karan. We have this Dan, Theodore, and our guest today, our very own Piero Molino. So today, Piero is going to be talking a little bit about declarative ML systems, especially with the software project that Piero has built around Ludwig. And so, as always, the plan is going to be Piero will give a 30-minute talk, and then we'll have a 30-minute podcast style discussion where you, the live audience, can ask questions. And during Piero's talk as well, you can continue to post questions in chat, and we'll keep track of those questions and get them across to Piero after his talk is over. Let me talk a little bit about Piero. Piero is a staff research scientist at Stanford working on machine learning systems and algorithms with Chris Ray. Before this, he completed his PhD in Italy, and then he founded a startup called Question Cube, and then worked for Yahoo, then worked at Geometric Intelligence, which then got acquired by Uber. And then he was one of the founding members of the Uber AI Labs, where he worked on pretty much every topic in machine learning. So yeah, so he's done a lot of stuff. So we're very excited to have him talk about Ludwig. So Piero, take it away.
Yeah, thank you so much, Karan. Yeah, when I was at Uber, I actually have been working on many different things, and actually that percolates into Ludwig too, to a certain extent. I will give you some, backstory about Ludwig, which probably will be more fun. So the way I'm gonna give this presentation is the first part will mostly be about introducing the tool, and the second part I want to talk about like some, again, backstory, motivations, and talk about what's coming next for the tool, because I'm really excited about it. So let me get started. What is Ludwig to begin with? It's a deep learning toolbox. It's particularly good for experimentation, in my opinion. It's based on top of TensorFlow, although you don't have to touch the TensorFlow at all for using it, because no coding is actually required. Ludwig provides you a declarative interface where you just give the configuration of what you want to do, of your pipeline, of your model, and that's all you need to actually train a model and use a model. You will see how in a minute. Right now, it's it was released as open source in 2019, and now it's relatively well established, and there's many companies using it, and also many universities are supporting it, and many integrations with different tools that I will touch upon later. The basic principles behind the architecture of Ludwig is that when I built it, I wanted to make it general. So I wanted to make it so that it could be used in many different machine learning tasks, because at that time I was working at Uber and I was working on many different machine learning problems. And so I needed a tool for myself to be able to jump from one project to another and ramp up in a new project quickly. I also wanted to make it really flexible so that both experienced users have a lot of control of the models and the pipelines that are trained, while unexperienced user can very quickly start to use the tool without a lot of deep knowledge. I also wanted to make it extensible, because every day there's a new deep learning architecture that comes out, and I wanted to make it so that people can easily add them to the ones that are provided in Ludwig. Deep learning models are kind of black boxy. I mean, there are studies that are trying to open the black box and make us understand more what's happening. What Ludwig provides you is a set of visualizations that make it so that you can understand at least the predictions that the models are putting out, and also compare their performances and understand how well they're performing. Also try to make it easy. I will show you both command line and a programmatic API that, in my opinion, are pretty easy to use. And finally, I wanted to make it open. Is released under Apache 2 license. So let's start with a simple example. In this example, we have some data, and the data looks like this. It's a table containing two columns. One is news and one is class. The news column contains some text, and the class column contains the class associated with that text. If you want to train a model with Ludwig and test its performance, all you have to do is to launch this command from the command line, Ludwig experiment, and then you provide the data, in this case in CSV format, but many other formats are supported. And then you provide the configuration. The configuration is can either be a YAML file or a string that is parsed in YAML. And here you can see it basically contains two main parts, the input features and output features. In this case, the input feature is a list with only one element, which is the inputs that we want to give to the model. The name is news because it's the same name of the column of the data, and the type is text because that's the way we want to interpret the data that is contained in that column. And for the output features, again, there's only one element in the output features, and that element has name, class, and type category. What happens when you run this command is that Ludwig first takes the data, splits it in training, validation, and test, but you can actually also provide the splits yourself if you want. Then it trains a model, validating on the validation set, and in the end, produce predictions and evaluates the model on the test set. This is what happens during training. You can see that this is every single epoch of training, you will see like a summary of the performance so far. And then at the end of training, you can see statistics that are calculated over all the test set and for each single class in the test set, for instance. So this basically was Ludwig in a nutshell, but how does it work under the hood? The architecture is pretty standard and straightforward, to be honest. The training part works this way. When you provide some data, let's assume it's a file containing CSV data, but it could be anything else. There's first a pre-processing step that pre-processes the data into tensors. And by doing that also saves some mappings that are useful later on for mapping some new test data into the same format. The tensors are then provided to the model building component that creates a model and trains it and produces both weights and the hyperparameters that describe the architecture that was trained and the parameters of the architecture. At prediction time, there's some new data, and this data is pre-processed using the same mappings that were obtained at training time. And the pre-processed data is provided then to the model that is loaded from the weights and the hyperparameters obtained at training time. And the model produces predictions and scores that then are post-processed, again, using the same feature mappings. For instance, if the model produces a prediction of class number 8, then these feature mappings tell us what is the label of class number 8 and produces a final CSV file containing all the predictions. And when you run the experiment command, Ludwig first trains and then predicts and evaluates the model. And what actually makes it pretty compelling, in my opinion, is that you have a data type abstraction. We've seen an example of that, but we'll see more about it, that allows the tool to be flexible towards many different machine learning problems. And then there is this declarative configuration that you provide to the tool, rather than having to actually write the code of the model or the pre-processing or the post-processing or the training yourself. And finally, there's a smart use of KV-args. I will show you an example of that. So let's step back for a second. Let's get back to our original experiment example. And this is the part, the highlighted part is the configuration. What actually happens when you provide this configuration is that it overrides some defaults and becomes this thing, which looks complicated, but I will show you examples of all these pieces, so it will be pretty simple. It's divided in 5 sections. Input features and output features, we've already seen it. You can provide more than one input feature and more than one output feature, so you can do multimodal inputs, you can solve multimodal problems, and also you can solve multitask problems because each single output is a different task. There's another piece called the combiner, and the combiner is a piece that takes all the inputs and provides them to the outputs, and I will show you some examples of that. And then there's a section for training and a section for pre-processing. What you can specify in the training section are all training parameters like the batch size, the learning rate, which optimizer to use, what's the scheduler for the learning rate, and so on and so on. And for the pre-processing, you can specify how to pre-process some different data types of data. One example is text. So for instance, for text, you can specify how big is the vocabulary, the maximum size of the vocabulary, or if you want to trim the length of the sentences that are provided as input to a specified length, a maximum length, then you can provide that into the pre-processing parameters. And the same is true for the other data types. But why do we need this input, combiner, and output architecture to begin with? So Ludwig provides, again, different data types that you can use, and each data type is encoded in a specific way, and each data type is also decoded in a specific way. The ones that are provided in Ludwig right now are text, category, numerical, binary, sequence, a vector, set, bag, image, time series, audio, speech, H3, which is spatial indexing system, and date. And so what you can do is you can combine and mix and match depending on the schema of your data and obtain a different, a model that solves a different machine learning problem. For instance, the example that we've seen so far had a text input and a category output. And so Ludwig will basically train a text classifier. But if you provide an image input and a text output, Ludwig will train an image captioning system. If you provide categories, numericals, and binary values as inputs and the numerical output, then you're doing a classical regression problem. And if you have, for instance, some audio input and some binary output, you can do speaker verification. And even more complex models, you can provide text as input and image as input and have binary as output, and so you can do visual question answering. As you can see, this architecture is really flexible and allows you to do many different things with a single tool. Importantly, each input feature can have multiple ways to encode the data, and each output feature may have multiple ways to decode the data. And I will not get into a lot of details for this. There's many examples on the website, but I will give you the example of the text inputs because it's one of the richest ones. And as you can see, there's at least 6 ways that you can encode inputs using a stacked CNN, a parallel CNN, a stacked parallel CNN, an RNN, a combination of CNN and RNN, and a transformer. And you can also use pre-trained models here. The way you go and the way you can use these models is basically specifying the keyword encoder in the configuration for your specific input, in this case, text CSV column name, and you will be able to use that specific encoder. Each encoder comes with its own parameters, and so you can change all the parameters associated with that encoder. When I was telling you about the smart use of KVArgs, this is the class that implements that encoder, the ParallelCNN, and the init function, you can see that all the parameters that are provided as input to the ParallelCNN are the same ones that are that you can provide from the configuration. So basically, by using KVArgs, Ludwig percolates all the parameters all the way into the architecture to the point where they are basically used inside the code that actually creates those components of the architecture. And if instead you wanted to use an RNN, all you had to do is to specify encoder RNN, and then the set of parameters that you have at your disposal change. Because, for instance, for an RNN, you want to say if it's bidirectional or not, or how many layers, or how big is the cell, the state size, or which type of cell to use, which are different from the ParallelCNN, and they're also different from the transformer, because the transformer has a different set of parameters in and on itself. So you have full flexibility here. You can change all the different details of the parameters. And this kind of architecture is particularly nice because it allows you to actually reuse encoders for similar data types. In this case, sequences, time series, and audio and speech can use the same encoders that were used for text. I will not get into the details of the other data types and how the decoders and combiners work, but if you're interested in that, there's plenty of documentation on the website. What I wanted to show you more is some example models that you can build with this architecture. This goes back to the original example of text classification. That command that you see on the right is all you need to specify to actually train this model. So you specify Ludwig experiment, the dataset, and the config, which contains just input features and output features with name news and with name class, respectively. And in the case of the news, you can see type is text and encoder, in this case, is ParallelCNN, and we want to encode text at the level of the words. If you want to have an image object classification, like, for instance, classifying ImageNet or MNIST, All you have to do is you have to specify the configuration with input features, and the name in this case is image path, because that's the name of the column on the left, and the type is image, and the encoder, for instance, we can use a stacked CNN, which is similar to VGG, but you can also use ResNet and other architectures. If you want to have a speaker verification system, let's assume that you have 2 speech files and you want to verify that they are coming from the same person, then you can have 2 different columns in your data with speaker 1 and speaker 2, so speech path 1 and speech path 2, and then a column that tells you if the speaker is the same or not, so true or false. The way to do it in Ludwig is you specify, as you can see on the right, input features, and in this case, the list contains 2 elements. One is as named speech path 1, and the other one is named speech path 2. They're both for type audio, but the second one has this tied weights parameters that make sure that you're using the same weights for encoding speech 1 and speech 2. And the output in this case is a binary, of binary type. This model is an example of how you can calculate an expected time of delivery. This was it's a simplified version of the model that we were using at Uber. And in this case, it contains 4 input features: the restaurant that you're ordering from, which is a category; the order itself, which is a bag of items, a bag because you can order one item more than one time. Like, for instance, I ordered 2 pizzas or something like that. And the hour and minute of the day when the order was made, which can be treated as numerical values. And then the expected time of delivery, the ETD, is also considered a numerical value. And for instance, you can specify which type of loss you want to use for optimizing this value, for predicting these values. And in this case, it's mean absolute error, but you can also use other losses that are provided by Ludwig. Another example is a Chit-Chat dialogue model where you have 2 users speaking to each other. In this case, you want to encode user 1 as text using, for instance, an LSTM, and then user 2 as text using, again, an LSTM, decoding it as an LSTM using a generator decoder. And in this case, you can also use attention. You can specify the type of attention that you want to use. If instead you want to tag an input sequence, like an input piece of text, then what you can do is you basically have to do exactly the same that you would do for a sequence-to-sequence model. The only difference is that instead of having a decoder generator that generates 1 token at a time, in this case, you use a tagger that basically for each element of the input sequence produces a single element of the output. Great, so these are basically many examples of what Ludwig can do. There's many more on the website. Now let's talk about a little bit how you can use it, and how you can also use it using the programmatic APIs, and what other features are actually available to you in Ludwig. First of all, installing it is very simple. You just have to do pip install Ludwig, and there are also some sub-packages that deal with specific data types. Like you can pip install Ludwig text, for instance, to add some text capabilities, or Ludwig image to add image capabilities. The programmatic API is very simple. In order to obtain a model, you just have to import the Ludwig model class from the Ludwig API package. Then you instantiate it, providing a config, and that config is basically can be a dictionary, or can be that contains the same content of the YAML files, or can be a file. Once you have a model instantiated, you can train it on some training data. You can also save the model and load it back if you want, and you can also use it for obtaining predictions on some other data that you want to use for obtaining predictions. After you train the model with Ludwig, what you can do is you can also serve it as a REST API by just calling Ludwig serve and providing the path to the model. In Ludwig, you also have the possibility to use a bunch of visualization commands. There's more than 20, and they allow you to both compare performance of the model, like for instance, the first one here, also compare the predictions, and also understand more about the performance of the model. The second plot here, for instance, is a calibration plot. The third and fourth are plots of coverage versus accuracy, where you increase a threshold over the confidence of the model, and you see how performance changes. The fifth plot is a comparison of the predictions of two different models. And the fifth one is a comparison of the accuracy or performance of the model against the frequency of the class that we are considering. There's many more available to you. There's more than 20. In version 0.3, we also added some hyperparameter optimization capabilities. And so assuming that you have a Ludwig configuration like the one that you see on the left, you can specify an additional hyperparameter section to the configuration where you specify which metric you want to optimize and which target you want to use, but also which parameters you want to optimize. And you can optimize any parameter in the configuration. So either architectural parameters, training parameters, or pre-processing parameters. And in this case, we're optimizing, for instance, for the number of layers, the learning rate, and the type of the optimizer, for instance. And you can choose the sampler. Right now we have random grid and PyShot, which is a Bayesian optimization algorithm. And you can also choose how to execute this optimization. For instance, you can execute it in parallel locally, serially still locally, or using fiber on a cluster of machines with Kubernetes. We also added an integration with transformers. So basically, when you can specify each of the models that are available in transformers as encoder. And so what Ludwig will do, will download it automatically and use it for encoding your inputs. And you can also fine-tune them if you want. You can do also distributed training using Horovod, as you may be familiar with, because Travis already told you about that a couple of weeks ago. All you have to do to run Ludwig with Horovod is add Horovod run and some parameters for Horovod in front of your Ludwig command, and the training will be run in a distributed way. We also have integrations with experiment tracking products like CometML and Weights and Biases. And all you have to do to track the training of your Ludwig model in those projects is just provide an additional keyword, which is either 1db or Comet. And finally, when I was talking about extensibility, in version 0.3, we refactored Ludwig so that now adding an encoder, for instance, is very, very simple. This is an example of an image encoder. All you have to do is to implement basically a layer. And this layer contains two functions, an init function and a call function. In the init one, you can put all the parameters that you want. And then in the call one, you can use those parameters and put any TensorFlow code that you want, as long as you respect the shape of the inputs and the shape of the outputs. For images, for instance, you expect the input to be shaped batch, height, width, and channels, and the output to be shaped batch and a new height, a new width, and a new channel. Anything that you want to do to transform from one to the other, it's up to you. So you can add your own new encoder very, very easily. Great. So now that I described the tool, I wanted to give you a little bit of a backstory about it and also tell you what's coming next for it. First of all, I started working on this about September 2016, so it's quite a long time ago. And at the beginning, I was using it for a visual question answering project. So already there were the image type of inputs and a text type of inputs from the very beginning. And so you could already train multimodal models with Ludwig in 2016. Then in 2017, I actually ended up using it for a customer support project called Kota. If you're interested, there's material online, there's papers and blog posts about it. And I also added the concept of data type, that specific type of abstraction. And the reason is that during this project, the product managers of this project came back to me multiple times by telling me that there were new input features that we had available for this customer support project. And also there were new tasks that we wanted to solve using the model. And so for that reason, I created this abstraction that allowed me to add new tasks and new input features quickly. And so multitask learning appeared in Ludwig around the beginning of 2017. Then in 2018, while I was working at Uber, the tool was used for many different projects. And so I added new data types, and I used it for prediction of expected time of arrival, also for entity extraction and for image classification, and also for identifying personal information in the database. And finally, for classifying queries to search queries with multi-label classification. And so you can imagine that because the number of tasks increased, also the generality and the breadth of the tool increased. And that's the reason why then in February 2019, we decided to release it as open source, because we believed that the tool could have been used by other people for many different tasks. So we wanted to give back to the open source community, because Ludwig itself is based on a lot of open source projects and open source tools. So it was the best thing to do, in my opinion. In July, we released a new improved version, 0.2, that contained an implementation, the first implementation of BERT, also the audio features, and the REST API and the visualization API. So it was a substantial step forward. But October last year, we actually released a version 0.3 that improved a lot the tool. In particular, the programmatic API, now it's much more robust and much better, it works really nicely. We moved to TensorFlow 2, which allowed for a more modular organization of the internals of the tool, because you don't have to deal with the global state that was there in TensorFlow 1. And we also added integration with transformers, and we added the hyperopt capabilities to the tool. And now, finally, this in the first half of 2021, we will release version 0.4. And so what's coming up with version 0.4? In particular, data preprocessing in Ludwig in version up until 0.3 was one of the main bottlenecks, because we were doing mostly in-memory data processing using pandas. Some specific data types, like images and audio features, could actually be stored in H5 files and streamed from disk, which was great. Although that didn't solve entirely the problem, because we wanted to make it so that for every data type, and you could basically do some streaming processing. And also we wanted to make it so that you could do it in a cluster, in a distributed setting. So what's happening right now in version 0.4 of Ludwig is that we basically abstracted away the data frame interface. And what happened by doing that is that now we can have multiple implementations, multiple backends, really. We still use pandas for when the computation happens locally, but now we're also adding Dask and Modin for having distributed implementations of the pre-processing or post-processing of data. And so basically now with version 0.4, you will be able to run post-processing and post-processing on a cluster and leverage parallel computing much, much better than you were able to do before. And also the other big piece of the changes that we are doing in version 0.4 is the integration with Ray. In particular, this distributed data processing that I was telling you about will run natively on a Ray cluster. And so this will be very, very handy for everybody who's ramping up with Ray right now. And also, we will have in the hyperparameter optimization a new RayTune executor. So now you can use everything that RayTune allows you to do with Ludwig automatically without having to do anything else. You just have to declare in the configuration that you want to use RayTune. And also, basically, all the sampling algorithms that are available in RayTune, you will basically be able to use them right off the bat in Ludwig, just changing one string in your configuration file, which is pretty handy. And so I'm pretty excited about this new release, which will come in the next few months. So another interesting thing that we're working on that will be released soon is a benchmarking suite. So when you start with Ludwig and you have a new dataset, you don't really know which architecture you should be using. Ludwig provides you with both some reasonable defaults and also the hyperparameter tuning capabilities that allow you to basically test many architectures and select the best one. But would be something that would be really more interesting would be to provide a default architecture that has been tested on similar data sets, and so you know that it will perform pretty well. So what we're building is like this crowdsourced benchmarking tool so that people can train many different architectures on many data sets with many hyperparameter settings. And we will collect this information to then having a capability in Ludwig so that given a new data set, it will be able to suggest you what a good architecture and a good configuration would be for that data set. You will be able to then, fine tune it and do some hyperparameter optimization if you want, but the starting point will be much better. And so because this will be, again, an open source component, we will encourage people to, provide the results of their benchmarks so that automatically, so that basically we will collect all these results together and we will learn all together and share the learnings with the community. So if you want to know more about Ludwig, there's the documentation available on the ludwig.ai website. There's also the repository on GitHub that you can go to, and 3 blog posts that introduced version 1, version 0.1, version 0.2, and version 0.3. And there's also a white paper that you can look at that explains a little bit of the reasoning behind the architectures. I usually end talking about Ludwig by thanking all the contributors, all the key contributors that helped me in this developing this tool. And in particular, I want to thank Travis, Yaroslav, Sai, Jim, Avanika, Ivilo, John, Doug, Patrick, Carlo, Chris, and Boris that have been super helpful so far. That's it. That's all I have.
Thanks, Piero. That was a great talk. Could you also stop sharing the screen? Thanks. Yeah, I guess if you're in the audience, you can definitely send more questions our way, and we will try to communicate this to Piero. So I guess to kick us off, maybe like towards the end of your talk, you talked a little bit about being a little bit data-driven in terms of looking at the Ludwig benchmark and then trying to understand what models might be suitable for a user that comes into the system. So I'm wondering, like sort of going a little bit more high level, like have you thought about how to think through some of these declarative primitives that are available to the user, right? Like right now, Ludwig works in terms of like defining some of these schemas, like input, output, and then helping the user spin up basically the middle part, right? And so here it seems like you're adding some more automation. But in general, I'm wondering what your thoughts are on where you think this is headed and whether there's maybe room for like a declarative programming language for machine learning, that kind of thing, where maybe I can say like, give me an image classification model that has like 85% accuracy on some like target data set or something like that. So something way more automated, and how do you see that kind of transition happening?
Right. So yeah, so this is to a certain extent one of the goals of this Ludwig benchmarking effort that we're running right now is exactly that. The interesting thing about it is that because we will be collecting some metadata information about the data sets and some metadata information about, some information about the architectures themselves, and also some information about how the architecture performs. So for instance, we want to collect all performance statistics, but also other aspects, like for instance, how long did it take to train, or how robust was this model with some out of distribution samples and things like that. Also potentially the carbon footprint of training this model, all these additional aspects. What I expect that we will get to is something that is exactly what you were describing. So where you can say something like, I have this new data set. Maybe it has images of this specific size, and the distribution of the images looks like this. What do you suggest? And Ludwig will tell you, well, there is this architecture that is for a data set that is similar to the one that you are describing, performed with 85% accuracy, for instance. So maybe that's what you want to use. But maybe you can also say, well, but this architecture that you're suggesting me is takes really long to train, and I don't have that amount of time or that amount of compute at my disposal. And so because of these different samples that we collected, we can say, well, if you put the constraint of, the architecture cannot train in more than 2 hours, for instance, then we can give you the best architecture that we know of, given those constraints. And so it could be like a really good starting point, I believe, for someone with a new data set and trying to get their very first model out of the door.
That sounds
kind of sounds cool, like a classic scheduling problem that you might run over in like an operating systems class or something. Kind of along those lines, I was kind of wondering, I know that you have some thoughts on this. Could you speak about what you see as the future of these more declarative systems in the future of research for machine learning? Throughout the history of computing, we've seen kind of research shift from everybody kind of doing low-level stuff like assembly or things like that to people increasingly having more high-level interfaces to these. Where do you see kind of that going in the future of machine learning, and where do you kind of see Ludwig on that path?
Right. That's a very interesting question. I would say that the way I see it, and again, we will discover soon enough if I'm right or wrong, but the way I see it is that with machine learning, we've been building for the last I would say 20 years probably. In most cases, very bespoke solutions to specific machine learning problems. And that made sense because we didn't know much about the whole development process, and we didn't know much about the problems that we would incur in, and we didn't have tooling, a lot of tooling supporting it. But over the course of these last 20 years, this tooling emerged, and also processes for developing these models emerged. And so I think that we are in a similar place where like databases may have been in the 70s, release bespoke solutions that were at a certain moment surpassed, or at least there was some new higher level abstraction, like in the databases world, could be in like relational database management system where you had like a declarative interface like SQL to interact with it. They made it so that a bigger set of people without a super detailed knowledge of COBOL now can finally use a database system. And that made so that database system exploded, and now they are they've become, in the last 50 years, like one of the most important things that we do with computers, really, in general. My take is that something similar is happening, or will be happening for machine learning too, where there will be this separation of interests between the developers that actually develop the systems and the people that are using them for obtaining predictions, and that will make it so that many more people will be able to interact with the systems at all. And finally, the role of Ludwig in this, I feel like Ludwig goes slightly in that direction, in the sense that its declarative configuration makes it so that it's easier for someone who has less detailed knowledge of deep learning to actually train these models, although I believe that there's still a lot to be done. And Ludwig is still a tool that is kind of aims still at the data scientist, while maybe for putting machine learning in the hands of the rest of the people, there's more work that needs to be done.
As kind of a follow-up to that, what do you think kind of changed in the last few years to where it's suddenly possible to start thinking about these higher level things, and we're no longer in the
Right.
I think you gave the analogy of the COBOL days of machine learning. Like, what's changed? Like, what's new that this is no longer the case?
Right. I think it is a combination of things. There's no single thing that happened. I would say on one hand, we have been building systems for the last 20 years, and so there are learnings from those systems, and now we can see patterns that are kind of common among the systems, and we can kind of finally, I believe, put these patterns together, and some commonalities among the systems emerge, and so now we know how particularly some types of problems should be solved. We have a process. We have learned our lesson into taking a research idea or a research machine learning algorithms and actually using it in practice in the real world. So I would say the clash between the machine learning research community and the real world application of machine learning has been one important factor. Another important factor is, as I said, the systems. And the other important factors is that now we can afford to waste a little bit of compute and be slightly higher level than we were before. And the same has been true, like for instance, for compilers. Like you could get to the point where if you are a good enough assembly coder, you could write some piece of code that is faster than a compiled C++ piece of code, but the amount of effort that it will take you is substantially higher. And so the higher level abstraction that a C++ compiler, for instance, gives you is, in most cases, a better trade-off in terms of your time and the machine time. And so I think that that's also kind of true right now, because now we have accelerators for machine learning models that make this possible, I believe.
So it's interesting that you talk about this cost that you have to pay basically to use a higher level interface, right? Like maybe you could do things a little bit more efficiently if you wanted to get into the nitty gritty, but it sounds like what you're saying is there are some trade-offs to using systems like Ludwig, which try to abstract away a lot of the underlying implementation details. So I guess, I mean, following on from that, how do users tend to respond to this type of interface? Like, I'm curious, you talked a little bit about the history of Ludwig and kind of how the progression was a natural development of like adding data types and features based on what users needed. It looked like it took many years to kind of build out those capabilities. But I'm wondering, like during that process, when you would like have users come in and try to use the system, like what are some of the things that you picked up on that made users uncomfortable or made users kind of more comfortable? And so like things like visualization, for example, I think you talked about how there's like 20 types of visualization in Ludwig, but I think one natural thing I'm thinking about is like if I use a system like Ludwig, I might not know what's going on underneath, and that is often a source of discomfort for users, right? Like they don't fully understand the process that's being executed underneath, and so like if things don't go the way that they want them to, they're kind of uncomfortable. They don't know how to respond to that. So have you thought about this process of both like how users respond to these types of systems, as well as your experience with that, and how you think maybe like you can support users to debug some of this at that like high level interface and not have to go into those details?
Right. So this is a very good question. And again, it's a matter of trade-offs. It's also true that in the history of computing, I think, well, it's not always, but in some cases we got to the point where actually the higher level interface, it became even a more efficient way to do things. Like for instance, again, to the example of compilers, I think there's right now really few, relatively few developers in the world that can write assembly code that is better than the code that is generated by GCC, for instance. So we got to a level of sophistication in GCC so that, the trade-off now shifts a little bit, even more towards GCC, right? Towards the higher level abstraction. Specifically for Ludwig, I would say what you give up, let's say, by using this higher level of abstraction is a little bit of control, but the fact that Ludwig actually allows you for fine-grained control on demand, let's say, fine-grained control of all the aspects of your architecture, makes it so that you could start using it, and then if something doesn't work as well as you want, maybe that's the moment for you like to learn a little bit, and Ludwig still provides you with a mechanism for controlling what's happening. And in terms of visualizations, actually the visualizations that Ludwig provides are more about the outputs and the relationships between the outputs of different models, so the relationship between the outputs and the ground truth, more than the specific of what's going on inside, because I imagine most of the users to actually be willing to, again, understand the behavior of the system from a holistic point of view, from a performance point of view, rather than the nitty-gritty details of like what was the distribution of the activations at that specific layer. And so in most cases, I would say for these kind of users, so I've seen both users using the Ludwig interface as it is and being happy with using like the default parameters. Other users going all the way down and changing a lot of parameters. So I've seen some very complex configuration files sometimes. And finally, I've also seen users that at a certain moment in time, they were more sophisticated users, but said, well, you know, I think I could get better performance if I had this additional encoder. And so they actually did a PR in the code and added their own additional encoder to the set of the ones that Ludwig provides, which to me speaks to the fact that an architecture like this could serve many different types of users in a slightly different way.
Hey, Piero, I have a question. You know, several years down the line, what's your most optimistic view of what Ludwig 1.0 will look like compared to, say, 0.4?
That's a good question. It's a very good question. I don't think I haven't thought it through all the way there, I would say. What I imagine is, I think Ludwig version 0.1 may look not substantially different from version 0.4 in the sense that I believe that with the pre-processing and post-processing and basically every piece of the processing, also the training and the prediction done in a distributed way, I think the efficiency aspects of Ludwig will mostly be taken care of. So what I expect to happen from, let's say, 0.5 to version 1 is more likely to increase the capabilities. So to add more architectures and having, this, for instance, suggestion of which is the architecture that would work better for your problem. These are capabilities that definitely we will need to want to have there, but also to have additional data types covered and additional data types in particular for the outputs, because for the outputs, not all the data types are supported right now, but I will want to add, for instance, images. For instance, text generation is already there, but I will want also to add image generation or speech generation. These sort of things that are doable. It's just that the team that is supporting Ludwig is a great community, but we have to be mindful of the priorities. So I imagine that in version 0.1 we will have implementation of inputs and outputs for all the data types that we care about, for instance.
Hey, Piero, I had a question. So we've had a lot of talks at the seminar about the kind of iterative development process for machine learning with debugging, maybe debugging your data, debugging the objectives you set or the model architecture, and maybe also analyzing and debugging the predictions that are coming out of your model. So I'm wondering whether and how that ties into Ludwig. Is there anything you can do since you have this higher level interface to help with that?
Yeah, so what I believe in particular is that because you have this higher level interface, you could make the whole process of iterating through models and also through data faster, because the single like link that deals with the model architecture can be made itself much faster, rather than writing your own thing and writing the preprocessing, etc. So if that piece is faster, then you can also have a tighter loop and get to hopefully a better performance faster. And another thing that we added in version, I think in version between version 0.2 and version 0.3, we added the capability of having soft labels provided to Ludwig, which ties really well with what Alex and Chip were talking about when we invited them about weak supervision. So in Ludwig, you can provide the let's say outputs that a tool like Snorkel produces as labels for Ludwig models. And so that loop of I have some initial data, I obtain some weak supervision, I train a Ludwig model for that, and then I go back to the data and maybe I manually either improve the labeling functions or I manually tag some of the data points and I keep improving, becomes very fast, because from getting from the point where you have the data to the point where you have a trained model, it's writing a configuration file for that is very, very simple. So that speeds up things substantially.
Makes sense, yeah. And when you look at users of Ludwig today, what are they spending most of their time doing?
Oh, I wish I knew. I mean,
okay, yeah.
Being it an open source project, what I get is mostly from the issues, right, and from the discussions that are there in the different channels that we have. I would say they spend most time iterating over models. Although I would, because that's at least the visibility that I have over their projects. But I will be really curious to look at where they actually, I believe that they will probably maybe spending a lot of time on data quality, but I don't have a lot of visibility on that, unfortunately.
Hey, Piero, we had a couple questions in the audience, and I was also kind of personally curious. I was kind of wondering how you see behavior differ across different target users, like the ML researcher versus the ML engineer, versus more like entry-level ML folks and PMs. And we also had a couple questions in the audience to like, what do you think is necessary to kind of support even more people in democratizing ML to maybe get to, the business analyst, the domain expert who doesn't have as much technical expertise?
Right. I would say the difference in behavior is, I don't see like a lot of difference in behavior. I would say what I observe is that, more expert people tend to use it as, a very quick way to obtain a baseline. And then maybe they have their own modeling ideas and they maybe have like a parallel kind of thing going on, developing their own model. And so they have basically a battery of tests with really strong baselines. And that's one way you may want to use Ludwig. And so that's what I see more expert and more research users do. While for other users that are more, let's say a little bit more entry level, they, in most cases, are actually, happy with whatever the result of the Ludwig model is in itself. And in some cases, I've seen people just, even if the serving capabilities of Ludwig are through Python, still for some use cases, that's good enough. And so some people even deploy the Ludwig models with our serve functionality. Although that sort of functionality, we didn't design it to be like the most efficient possible ever, but for some use cases, it's actually efficient enough, and that's good. For the second piece of the question, like what do I see, what is still needed for reaching out a wider audience? I think that there is like still a gap in understanding of really basic concepts that in machine learning you cannot do without. Like for instance, even the basic concept of training. The fact that you need some examples to give to the model to be able then to use the model for obtaining predictions. I've seen some users providing a configuration file and then expecting, given some data, to obtain the predictions without having trained it. And so obviously that's not going to work. And so I think that's still a gap in understanding that higher level, let's say, users with less sophistication in machine learning will have to bridge to a certain extent. But also in terms of interface, I think the overall concept of having a model and training a model, it's a concept that we could potentially abstract away and get to the point where if I'm not interested in how the model is trained, but I'm only interested in the predictions, for instance, then I can directly use a model for obtaining those predictions without the need for anything else. And that could be, promising direction, because if you think about databases, that's similar to running queries without actually knowing which indexing algorithm were used for organizing that data inside the database. So I think that that's kind of a separation of interest that we could introduce in machine learning.
Yeah, I guess as kind of a maybe last question, I wanted to also get your perspective from the creator end, right? Like as the author of a software library that's pretty widely used. And as someone who's actually worked with data from images to text to time series and tried to kind of consolidate and build a single pipeline for those, what are some of the things that you think were most challenging about building Ludwig? I think one of the things that I think most people find challenging is data, right? Handling different data types, building out different data pipelines and so on. So some of your experiences just in building out the software project and what do you think people could kind of take away as lessons for those who are also building their own software libraries or trying to build tools?
Right. So that's a great question. I think two are the main challenges in my opinion. One is as you said, that heterogeneity of the data types that Ludwig deals with. Despite the fact that I actually worked with many of these data types, I haven't worked with all of these data types, and direct expertise reveals a lot of how you have to massage the data and how you have to build models for that. So from the perspective of a maintainer of the project, of the creator and maintainer of the project, that's a challenge for me. So I have, let's say, to study a lot of topics that are also a little bit outside of my comfort zone in order to be able to support those. But thankfully, the community has been great with that. So for instance, the audio features that I've never done anything with audio, but they were contributed by Patrick, for instance. And so, that's a great aspect of running a project as an open source community. And another aspect which is kind of tricky, let's say, is the fact that for building multimodal and multitask models, you have to take care about, make some assumptions of what are the shapes of inputs and outputs of all the components that you are putting together. And what helped me there was to kind of define types, in this case, internal types, and those internal types are treated as, tensors with specific shapes that I know of a specific rank. And so what was interesting there is that I think there could be an opportunity for introducing a little bit more stronger typing into machine learning in general. The advantage of having dynamic types is that you can get something done very quickly and prototype something very quickly. But most of the errors that you would encounter by building something like Ludwig are actually, weird shapes that are coming out from encoders that you were not expecting. And so if you impose some interfaces, and these interfaces are types that tells you how many dimensions, what are the names of those dimensions, and what are the ranges that are available to you, then that makes your life easier in the long term. And so that's one thing that I personally, a lesson that I learned, I would say, that I could share with everybody.
Awesome. Yeah, that was great, and thank you so much for answering so many questions. Yeah, since we're at time, I want to thank Piero. I want to thank the audience that tuned in.
It was fun to be on the other side.
Oh, sorry, what?
It was fun to be on the other side.
Yeah, it was. Yeah, we got to see you on the other side a little bit, so that was great. Hopefully you enjoyed it, and that will tell us whether our speakers also enjoy being on the other side. But yeah, I want to thank the audience, and definitely go to our website, mlsys.stanford.edu, sign up to our mailing list, and subscribe to the channel. Next week, we're going to have Anna Goldie talking about reinforcement learning for hardware and chip design. So tune in next week. Thanks, everyone. See you.